We are continuing our discussion of rotation by looking at inertia and Newton's second law. We're still dealing with cousins, these slight changes for the things we've already learned, things about motion, things about forces. All right, we're now looking at the inertia cousin and Newton's second law cousin. All right, so let's jump right in. To understand the idea of inertia for rotating things, I have an example that we're going to work through. We're going to prove it mathematically. I don't think the math is that difficult, so we'll do it. But we know, for example, in our old method, that inertia is measured by mass. That's what we said way back when. Okay, Newton's second law, the sum of the forces equaling ma. All right, the net force is based on m and a, or more relevant, the acceleration is based on how much total force, and the mass, this is a measure of the inertia of an object moving in a linear fashion. Well, rotating objects also have inertia. However, and this is the reason why we of course have a video about this, it's not exactly the same thing. Rotational inertia isn't as simple as mass. There's more to it. So this inertia of rotating things, it's known as two different terms. The first term is moment of inertia. That's kind of the old term, which is very unclear to me. All right, moment refers to how we measure things and the idea of things rotating. I don't think this is a very good label for this thing. This is much better, and luckily the AP Physics 1 test uses this label. I feel like a lot more people are using it. It's more intuitive. It makes it clear what you're talking about. It's known as simply rotational inertia. All right, but just know you might see in textbooks or in future courses this phrase, moment of inertia, but it's the same thing. It's the inertia of rotating objects. And here's my diagram to figure out what this rotational inertia is equal to. I have a toy plane on a string, but our setup is a little different than our circular motion. Okay? This is not being moved in a circle simply by tension. This is not someone holding a string and just whipping around some boring, simple object. This toy has a little propeller, or you could maybe imagine it has a little engine that's applying a thrust. The plane itself is applying a force. That's what this Ft, they have it labeled as the thrust force. Not to be confused with tension. We're actually not looking at this. Okay? We're going to be looking at the rotational aspect. Therefore, we're going to look at the torques. The tension force, if you remember, isn't applying a torque. So this is a force actually from this toy that's propelling it, that's pushing it in this direction. And it's a certain distance away. All right, from this, we can treat this as a point mass. We can look at the torques of the object and therefore get a better understanding of what this rotational inertia is. Okay, I promise it'll make sense. So I'm going to go to a blank slide. All right, here again is that diagram. I'm going to look at the sum of the forces, not in the centripetal. I don't really care about circular motion right now. I want to go back to kind of our beginning linear motion examples, things moving in straight lines. Because, of course, for some very, very tiny displacement, the plane goes here to here. It has a really tiny amount of horizontal displacement. So we're going to look at that. The forces that are acting horizontal, of course, this is a bird's eye view. If we were on the ground with the person, it would look like this plane is moving horizontally from right to left. So let's look at the force that's acting on this plane. Again, not the torque, or I'm sorry, not the tension acting inwards. The force is along this line. There's only one of them. It's this Ft, this thrust force. And we know that that force is equal to ma. And I'm going to label this mat. That's the tangential or linear acceleration. Okay? What if I ask you about the torques acting on this object? Well, again, there's not a torque from the tension. Okay? If we're caring about this object moving in the horizontal, we're not going to worry about the torque from the weight. There's only one torque that's acting in the horizontal direction, and it's the torque that's caused by this Ft. So there's only one torque, and that's caused by that force, F with little t. And what is that torque equal to? That torque is, of course, equal to that force, and that is already perpendicular, times r, how far away that force is acting. So the torque, I'm going to drop this Ft. Well, this Ft is going to be equal to mat. I got that just from right here. Plug that in, multiplied by r. Okay? Well, I know there's a relationship between tangential acceleration and angular acceleration. And again, that's the whole point of this video. We're trying to find the cousin. So at some point, we kind of got to translate things, these linear values, into the angular values. The tangential acceleration, if you remember from our last video, is the angular acceleration multiplied by r. So if I plug this in right here, I'm left with tau is equal to m alpha r, this whole thing was in parentheses, these parentheses right here, times r. Well, if I multiply that and I kind of rearrange my terms, again, just based on the convention, tau is going to equal m times r squared times alpha. Does this look familiar in any way? It's similar. It's a cousin of Newton's second law that we learned about. The force, the net force, is equal to ma. Force, the cousin of force. Here's linear acceleration, here's angular acceleration. This term right here is the inertia of things moving in straight lines. This right here is the inertia of rotating objects. So this is what we call rotational inertia. And it has a letter symbol, uppercase letter I. This is the inertia for rotating things. Notice it's a little different. Yeah, there's still m, there's mass in there, but also r, the distance from the hinge. And essentially the hinge is right here, right? The object is moving around and around. It's based on m and r. So what we have is Newton's second law. That's essentially what we just derived. There is only one torque acting in this diagram right here, but in general, the net torque is equal to the rotational inertia times the acceleration, just like the net force was equal to the inertia of an object times its linear acceleration. This equation is obviously just another form of this one rewritten here, describing what affects an object's acceleration. It's based, of course, on how much total torque and the inertia of the object. And here, this diagram, this is just a snapshot of what is shown on the AP Physics 1 equation sheet. So just make sure you've written down at least one of these on our diagram. But now we know Newton's second law for rotating things, and not just the static equilibrium when these torques all balance out. Now we can apply what happens when the torques do not balance out. When there's an overall net torque, it's equal to I times alpha. All right? Now, the rotational inertia of the object is, again, because this is a crucial idea, based on m and r. I is equal to m times r squared. And we just derived it for that single point that's moving around and around. That's also similar to just a simple hoop that's spinning around and around. All right? The exact value, however, of this equation actually changes. We had it, we derived it for that point, but depending on the object that's rolling, is it a cylinder? Is it a solid sphere like a bowling ball? Is it a hollow sphere? Is it a hollow cylinder? Is it like a door that's rotating? This equation actually can change slightly. It's always actually going to have an m and an r squared, but there's going to be a different fraction right here. But that's entirely based upon the shape and how that object is rotating. Okay? You're only expected to really know this relationship right here. The inertia is based on mass and this r squared. For different shapes, like I said, you might have a different coefficient essentially right here, but you wouldn't be expected to memorize that. In fact, I have here a diagram just showing some examples of different objects. I said that a hollow hoop has a similar derivation, mr squared, but notice, here I have a thick, wide cylinder. And we have a slightly different coefficient. And yeah, we're looking at a change, or actually an addition of r's here, but we still have an m and an r squared. Here we still have mr squared, but there's a different fraction. mr squared, different fraction, m, now the length squared. But again, that's that rotational axis. Okay? You are not expected to memorize any of these. You actually need calculus to derive these. And unless you're taking the AP Physics C exam, you don't really need to know the calculus of how we solve these types of problems. These would all be given to you. Okay? But again, the crucial idea is that you recognize this. The rotational inertia is based on m and r squared. In fact, we have to make sure we understand, this is my last slide, what this r is referring to. Again, here's my equation. I equals mr squared. It's tempting to simply think this is the mass of the object, this is the radius, the length or the diameter of the object, but that's really not the case. All right, the calculus definition is actually you doing an integral of the sum of the masses. Imagine adding up the masses at all the different locations of the object. R is not really just the distance or the width or the length of the object. This is a key idea. R refers to how far away that mass is distributed, and that is not easily conveyed in this equation. That's what can make this a little tricky. And I have an example for you. Imagine I have a meter stick, and I've attached kind of two blocks to it. I have a block at one end, a block at the other end, and here's a person's fist. I found this clip art online. Okay? And the person is just going to rotate it. Imagine taking your hand and going back and forth and back and forth and back and forth, rotating, pivoting this meter stick with these masses to one side, then the other, then one side, then the other. And imagine I repeated it, but now I put these blocks closer in. Just by looking at this equation, you might think these two things have the same rotational inertia because they have the same mass, same meter stick, same blocks, same meter stick, same blocks. Even the length of my meter stick, of course 100 centimeters, is the same for both. If all you think of this is in terms of the overall mass and the overall distance or length of the object, you would say that these two items have the same rotational inertia, but you would be incorrect. This object has mass that's located closer. Mass is located closer, which means a lot of this mass, these blocks, have a smaller r. So yeah, it's mr squared, but this is referring to the distribution of mass. This object here, IB, has a smaller rotational inertia than IA because its mass is located a smaller distance away from the center. Of course, we were, in this example, rotating it about the center hinge. So going to my question, which is easier to rotate? Well, if you think of the difficulty to rotate, maybe you're thinking, how much torque do I have to apply? Well, that's based on I times alpha. Well, in B, I have a smaller amount of rotational inertia. So if I apply the same torque, so tau A and tau B equals I. Here's IA, here's IB. I'm sorry, oops, B. Here's alpha A, here's alpha B. If I have the same amount of torque, because I'm the same strength for each one, I can twist my hands back and forth with the same strength, I'm going to be able to have a larger acceleration. I can get this one spinning faster, back and forth, back and forth, back and forth, because there's less inertia. Whereas this one has more inertia. Therefore, if I'm applying the same torque, I can't get it to accelerate as much. Back and forth, back and forth. I can really feel the stress on my arms. So that's the last idea for this rotational inertia. Again, you don't need to know the math. You don't even are expected to know or memorize all those different formulas. You are expected to know what it's based on, the mass and distance, and what's a little tricky, that this equation is really describing how far away the mass is located. That's the tricky part about this equation. But that's rotational inertia. We are using this when we talk about energy as well as momentum, so it's an important concept. And of course, we just learned how to apply it for Newton's second law. Thanks a lot.